to talk about a few different related topics today. The mean value theorem for derivatives, increasing and decreasing functions, and antiderivatives. So we'll start with the mean value theorem for derivatives. And this can be found on page 200 of your book as a full statement, but I will show it out here just to talk about it for a minute. Given f of x is a continuous function on the closed interval x between a and b, and is differentiable, or in other words, its derivative exists everywhere, differentiable on the open interval x from a to b, then there exists a value c between a and b such that the derivative at that value of c is equal to basically the average value of the function, or the slope of the line connecting the endpoints of that function. If I wanted to show this with a diagram, although your book has a fairly decent one on page 200 as well, let's say that I hit a value a here, and then I do something wonky up to here. I'll get real fancy and I'll change colors. If I draw a line connecting my endpoints, then the slope of this line would be given by this statement. The mean value theorem for derivatives states that on your overall function, there has to be some point c such that a tangent line to the function at that point has the same slope. Oh, that's a terrible straight line. If I think about it a little in terms of local geography, let's say that it's about 50 kilometers from Tadenwigers to Truro. And you, traveling at an inappropriate speed, tell me you can get to Truro in half an hour. You really shouldn't be able to do that in half an hour. But if you do it in half an hour, then your average speed would be 100 kilometers per hour. Now, what the mean value theorem says is that that means that you had to have been traveling exactly 100 kilometers per hour somewhere in your travel. Not that you were traveling 100 kilometers per hour all the time, but that at least one point in that travel you had to be going 100 kilometers per hour. That is effectively your mean value theorem for derivatives. Assuming a continuous function, you traveling to Truro, unless you somehow manage to teleport yourself there and break any number of laws of physics. If you go to Truro along a continuous path and don't break any laws of space and time, then your distance is a continuous function. The rate of change of that distance between my two endpoints, if that averages out to 100 kilometers per hour, then that means at some individual point you had to be traveling 100 kilometers per hour as well. And again, this is the mean value theorem for derivatives, and is also outlined on page 200 of your book. So, a bit of an example of working with that. This is example 1. off of page 200 as well. At least that's where it starts out. Show that the function f of x equals x squared satisfies the hypothesis of the mean value theorem on the interval between 0 and 2, and then find c such that f prime at c equals f of b minus f of a over b minus a. So for the first statement, that this satisfies the hypothesis of the mean value theorem. So to satisfy the hypothesis, the function has to be continuous on the interval and differentiable on the interval. X squared, it's a parabola, so we know that it's going to be continuous everywhere, so it's certainly continuous on that interval. And we also know that its derivative exists everywhere and is also continuous everywhere, its derivative. So it satisfies the two main hypotheses of the mean value theorem for derivatives. Therefore, there's got to be some place where this exists. So let's work it out. The derivative of my function is 2x. F at 2 is equal to 2 squared, or 4. F at 0 is equal to 0. So I'm looking for where 2x equals, or I should say 2c, equals 4 minus 0 over 2 minus 0. Or 2c equals 2, or c equals 1. Or in other words, when x equals 1, the slope of f of x is equal to the slope of the line connecting the endpoints of f of x. And so that is satisfying the mean value theorem for derivatives for this particular function on this interval. All right. Next topic as far as derivatives are concerned and graphing, which is what we're really getting into here. Okay, I'll go high tech here for a second. And we'll deal with increasing and decreasing functions of graphs. Increasing and decreasing intervals of functions. So, we say that a function f of x is increasing if, as x increases, f of x increases. If you were to look at it on a graph, basically you'd say that as the graph reads from left to right, the function also goes up as well. This would be an increasing function on this interval. And similarly, a decreasing function would be the opposite. I'll just write it out. For a decreasing function, as x increases, f of x decreases. But this all ties back to slope. If I look at this line, everywhere along it the slope is a positive value, which is indicative of an increasing function. So a function is increasing at a point x if f prime of x is positive. Similarly, function is decreasing if its derivative is negative. And this lets us outline intervals of increase and decrease for a particular function. And I'll just jump right into an example discussing this. This is example 6 on page 203, where we are given the cubic function x cubed minus 4x, and we're asked where it is increasing and where it's decreasing. You might also see that find the intervals of increase and decrease. So I'm going to look at the derivative of this thing. Its derivative would equal 3x squared minus 4. So I want to find out where the slope is positive and where the slope is negative. And to do that, I'm first going to talk about where the derivative is equal to 0. Running through this, I would get that 3x squared would equal 4, or x would equal plus or minus root 4 over 3, or, if you like, plus or minus 2 root 3 over 3. So these are the values of x that make the derivative equal to 0. Since my function is a polynomial and continuous everywhere, that means these are the only places where the derivative can change sign. So we set up a few intervals. From negative infinity to negative 2 root 3 over 3, from negative 2 root 3 over 3 to positive 2 root 3 over 3, and from 2 root 3 over 3 to infinity. So the reason I've set up my intervals like that is because since negative 2 root 3 over 3 and positive 2 root 3 over 3 are the only places where this thing can change, where my derivative can change to positive to negative, then that means any value for my slope in here, if I pick any point in here and the slope turns out negative, it's going to be negative everywhere in this interval. If the slope turns out to be positive, it's going to be positive everywhere in that interval. So negative 2 root 3 over 3, that is a little bit more than negative 1, or a little bit less than negative 1, I should say. So let's find the value of the derivative at negative 3, just to make sure we're in a good place. That is equal to 3 times negative 3 squared minus 4, which is 23. Positive number, therefore increasing function. Between negative 2 root 3 and 2 root 3, a nice easy number is 0. Negative 3 times 0 squared minus 4, which equals negative 4. This is a negative number, therefore it's decreasing. And then finally, I'll check one above 2 root 3 over 3. and I end up with 23 again in this case, which is a positive number, therefore increasing. So, how would I show this? I'm going to use interval notation, which I believe I've used a few times before, and I would say that the function is x is increasing on x from, it's everywhere in this interval, so from negative infinity to negative 2 root 3 over 3, joined with everything in this interval, 2 root 3 over 3 to infinity. And it is decreasing in this central interval from negative 2 root 3 over 3 to positive 2 root 3 over 3. So this is how you can tell where a function is increasing or decreasing. So this cubic function is increasing from negative infinity up to negative 2 root 3 over 3 and from 2 root 3 over 3 to positive infinity. It's decreasing between those two values. All right. One last little topic to hit upon. And that is the concept of the antiderivative. And what we say is a function, capital F of x, is an antiderivative of lowercase f of x if capital F of x equals, I wrote that wrong already, the derivative of f of x equals lowercase f of x. Moderately straightforward statement. A couple of quick examples. Is f of x equals 3x plus 4, an antiderivative of f of x equals 3. Quickest way to find out is I take that derivative of this is equal to 3, which equals f of x. Therefore, f of x equals 3x plus 4 is an antiderivative of f of x equals 3. And that was a fairly straightforward one. Sometimes you've got to do a little bit of work to work backwards through some of these. And, as I do sometimes like to tie these back to physics, and our textbook so nicely lets us, why don't we? Example 8, off page 205. We are asked to find the velocity and position functions of a body falling freely from a height of 0 meters under each of the following conditions. A. Acceleration is 9.8 meters per second squared. And the body falls from rest. And our starting height is 0. 0 at t equals 0. And we're also taking down as positive. So this implies a few conditions. If I have S, V, and A as my position, velocity, and acceleration accordingly, I know at t equals 0, S equals 0 from here. If the body falls from rest, I also know at t equals 0, V equals 0. And quite generally, I know my acceleration is 9.8 meters per second squared. Now, the relationship we've talked about is V is equal to ds dt and A equals dv dt. So, I'll start here. If acceleration is the derivative of velocity with respect to time, then that would also mean that that would mean that velocity is the antiderivative of acceleration. Two ways you can look at this. Acceleration is the derivative of velocity, or velocity is the antiderivative of acceleration. So that would imply that my velocity has to be the antiderivative of 9.8, with my variable being t. So I'd argue that my antiderivative will be 9.8t plus some constant. And we don't know what that constant is, but you could have any constant tacked onto the end, and the derivative of this would equal 9.8. And that is where our initial condition is going to become important. At t equals 0, v should equal 0. Therefore, 0 has got to equal 9.8 times 0 plus c, or c itself also equals 0, and your velocity is simply 9.8t. Now, I can have the same sort of relationship between position and velocity. My antiderivative of this statement, and this one gets a little trickier, but my derivative of s has got to end up being 9.8t. That means s has got to have a t squared in it. But when I take a derivative of this, I'm going to bring a 2 down. So 2 times what would give me 9.8, and that's going to be 4.9. So the derivative of 4.9t squared is 9.8t, but I could have some other constant tacked onto the end. And I know at t equals 0, s equals 0. So 0 equals 4.9 times 0 squared plus c. So c also equals 0 in this case, and s equals 4.9t squared. Now that was the A part of this. There's a B part, which is similar. The only thing that's really different are your initial conditions. Instead of being dropped from rest, it is thrown down with a velocity of 1 meter per second squared. So I still have the same condition on position, but my condition on velocity now is that it's going to equal 1 at t equals 0. So, once again, my acceleration is 9.8 by itself. So my velocity is going to be 9.8t plus a constant. Going off my initial condition, 0 is going to equal, 1 has to equal 9.8 times 0 plus c, or c equals 1. And my velocity is 9.8t plus 1. Bringing that through to position, my antiderivative here, the antiderivative of the first term will be the 4.9t squared for the same reasons as before. The antiderivative of 1 would be t, and then I have another constant stuck out on the end, but at t equals 0, s equals 0, so 0 equals 4.9 times 0 squared plus 0 plus c, or c equals 0, and my position is given as 4.9 t squared plus t. Or if you like, 1/2 acceleration delta t squared plus initial velocity times delta t. Alright, that's antiderivatives in a short form. There'll be some questions posted in the Google Classroom to try, and that's it. Thanks, everybody.